Hi, Devik. Hi, good afternoon, everyone in UK, and good evening in India. Uh, it's today. Today, it's a fantastic, a fantastic idea is on board with the collaboration of TAIym and BTSYM. I am Sandeep, chair for Tunneling Association of India Young Members, and today we have a very interesting talk from Trelleborg. And I would like to thank BTS and BTSYM to uh, to be in the support of this idea and allowing us to collaborate to do this talk. I think there's a huge potential in these type of collaboration when two different countries come together to share knowledge. Uh, this gives an opportunity to network with each other, know the uh, type of work we are doing, type of designs, type of construction practices we use. It gives an opportunity to develop and strengthen business collaborations. It engages young members early on with the global collaborative exposures and do cross-country exchanges of ideas. So I think this opportunity has huge potential, and we we should see such collaborations much often in coming future. So with this, I hope you'll enjoy the talk for today. And now I will hand it over to Divik to introduce the speakers and to hand over for the talk.
Thanks for the kind words, Sandeep. Also, I would like to reflect similar sentiments to what you have reflected. So thanks are also in order to you and also TAIym for your willingness to engage with us and initiate these collaborative endeavors. We hope to deliver more joint events in future, of course. So let me introduce myself to all those who are listening. I'm Divik. I'm one of the sub-chairs at BTSYM, and I head the professional development subgroup responsible for delivering these events. Similar to TAIym, we run a series of lectures which we have had to move online for obvious reasons. We, along with the BTS main committee, now maintain our recorded as well as future lecture catalog on YouTube. So please do subscribe to our YouTube channel and press the bell icon to stay up to date with our offerings. We have more lectures planned over the coming months, a few of them with other ITAIym member nations like the Canadians and the Brazilians. So further information about these will be made available on our social media platforms in due course. You can find us through various social media links and handles mentioned within the current slide, which is on your screen right now. It was during our BTSYM events that we met members of Trelleborg. Since then, they've become quite supportive of our endeavors and have delivered presentations at our evening lectures and conference, whilst bringing across the experience of immersed tube tunnels, something which we seldom talk about here in the UK. When we started planning this joint event with TAIym, our Dutch friends appeared to be the perfect choice for transferring knowledge related to something which might be relatively new for both BTSYM and TAIym members, but also because Trelleborg themselves, as I gather, have a strong presence in India through their design offices. This effort of ours is therefore a paradigm of international knowledge share unique to our industry. So without further ado, let me introduce our speaker for today, Nicas Brink. Nicas is a design engineer for immersed tunnels at Trelleborg, Ridderkerk. He holds a master's degree in industrial design engineering after graduating from Technical University Delft in 2017. During his study and career, Nicas has been involved in various fields of engineering, such as design of medical devices, mechanical design, and product development within the civil market. During his time at Trelleborg, he has been involved in several large immersed tunnel projects in which he gained both theoretical and practical knowledge. Today, he will share his experience on how to use rubber as a building material in order to make immersed tube tunnels watertight. During the Q&A, Nicas will also be joined by his colleague Joel von Stee. Joel is also a design engineer at Trelleborg and is responsible for the design of all tunnel seals within their infrastructure division. Prior to joining Trelleborg, Joel finished a BSc degree in mechanical engineering at the Technical University of Rijswijk in Netherlands. After this, he gained over 10 years of international experience at rubber products design, manufacturing, testing, and implementation. Joel has been responsible for over 15 tunnel seal designs on notable projects. To name a few, the Hong Kong-Zhuhai-Macau tunnel link, the Sha Tin to Central link in Hong Kong, the Midtown tunnel in Virginia, USA, and the Second Koon tunnel in the Netherlands. Joel also has experience of designing seals for sluices, dams, and tunnel rehabilitation projects. So without taking further time, I'll let Nicas start his presentation. It's over to you, Nicas.
Well, Divik, thank you very much for this kind introduction. It's an honor for me that I can today share my knowledge and experience within Trelleborg. As Divik already mentioned, my name is Nicas van der Brink. I'm design engineer at Trelleborg Ridderkerk, and I'm responsible for the immersed market. So today I will be talking about how to design rubber products to make an immersed tunnel watertight. So thank you. Thank you, Divik, for your kind introduction. Today I will be talking about how to design rubber products to make an immersed tunnel watertight. As already mentioned, my name is Nicas van der Brink. I'm a design engineer at Trelleborg Ridderkerk, and today I will talk you through. So, at first, I will give you a small introduction for the company I'm working for, which is Trelleborg. After that, I will dive a bit into the history of immersed tunneling. Where did this technique come from, and where does it lead to as we are today? Further on, I will talk a bit about immersed tunnels, what it actually is, what it entails. And after we have get a glimpse of the whole working principle, I will dive a bit deeper in the building material rubber. So what is this rubber, and why is it such a trustworthy material that we can use to engineer our constructions with? At last but not least, I will show you some practical information on how we can design these kind of rubber seals and how we can apply them in the in-situ situation. So, Trelleborg Group is quite a big company. It's the world leader in engineered polymer solutions. It was founded in 1905. It has about 24,000 people working for it. So it's a rather large company. It's represented in over 50 different countries and has over 120 different manufacturing facilities. As you can see Trelleborg products literally from space till seabed, from larger and smaller different type of products. We, however, in our business unit are mostly within those two fields, as shown over here, in the oil and gas industry and also in the infrastructure and construction business. So here you see an overview of the business unit Trelleborg Ridderkerk is part of, which is Trelleborg Marine and Infrastructure, which contains the marine fenders industry, the marine technology and infrastructure. So we are part of this infrastructure company, which is this one. I'm not sure what your geographical knowledge about the Netherlands is. That's why I showed a big country map of the country we're living in. And the company of Trelleborg, Ridderkerk, is located where the big red arrow points at. It's basically located at the perimeter of Rotterdam. And it's the business that it entails has to do with immersed tunnels, underground construction, energy, dredging, water management, and noise and vibration businesses. So we are here already for more than 140 years, so we have quite a lot of experience. And on these pictures you can see some key projects we've been involved in. So that is, for example, immersed tunnels on the right side, the storm surge barrier, and you can see the Erasmus bridge where we created the bearings for. The immersed tunnels we have been part of, that we actually delivered our products for, are can be seen in this geographical spread of the immersed tunnel projects. You can see that there is a large concentration of immersed tunnels happening in Europe, but also in Asia. There's also quite something going on over there. And we see a small concentration in North America. So those are the three major markets that use immersed tunnel technology. As I mentioned, I'm design engineer, and these 4 products are some key projects I've been involved in. 2 of them are very big Chinese projects, which is the TAIym Bay link on the upper right picture. Underneath, you can see the Shenzong link, and both of those tunnels are still being constructed as we speak. A bit older tunnel is the Goldbrookzoom tunnel in Denmark. That one was mainly a renovation project. And one below is the most flood protection project in Venice, which is designed to keep the water out of the city. So let's dive a bit into history. It all started out with the TAIym tunnel. So I think a lot of people already know about this tunnel, which is a quite famous one. It was the first time that there was a need to build a tunnel under a waterway, which was the Thames. So back in the day, London was a big metropolis. There was a lot of business going on, and there was a need to cross the waterway in order to arrive to the docks. However, a bridge was not suitable for that application, as it would stop the sailing boats from entering the city. So they needed something else, and that's why Mark Brunel first made a tunnel under the Thames under a navigable waterway. However, this was still a bored tunnel, so it was still not the beginning of the immersed tunnel construction. That started around at the same time in 1810 by Charles White. These pictures over here depict it quite well. The idea was to create a brick construction, a brick capsule, and lower that into a trench. The idea was to interconnect those capsules in a row to make one big interconnected tunnel on the bottom of this waterway. However, this was never been put into practice due to various reasons. And the first physical proof that the concept really worked was in 1893 with the Boston US sewer tunnel. However, it was still not a tunnel that can be used for human transportation. That happened actually later, about 20 years later in Detroit in 1910. So this picture shows how that tunnel looked like. It was a steel tube tunnel, a double one, and you can still see today as it is still in use between Windsor and the city of Detroit. So this project is a bit closer to home, in my hometown of Rotterdam. Here you can see the creation of the metro tunnel. It's being constructed due to cut and cover construction, so it was not lowered down, but it was actually made on site. And on the right side, you can see the first GINA rubber product that we created in Ridderkerk that was actually applied within this construction. The nice thing is about the story that during renovation work, we received some samples of the GINA seal gasket and other rubber products back from the tunnel owner, which provides us very valuable information about the lifetime and the rubber qualities over time when you place it into a situation like this for more than 60 years. So I will come back to this GINA profile and the properties of the rubber material that it has after a certain amount of time. So what's the principle of immersed tunnels? Let's take a look at that. So basically what's going on, you create a typical tunnel element out of concrete between 100 and 200 meters long. You construct such an element on a dry dock or somewhere else. When those parts are finished, you will float them up and you will bring them to the right location by using pontoons. You can see that in picture number 1. When they're on the right location, you have to lower them and you place them on the ground. So in number 2, you can see 2 tunnel elements adjacent to each other lying on the trench of a waterway. You will need to use initial mechanical jacks in order to initially compress them together. And by doing so, you have the first connection between the 2 elements. In number 4, the vertical gray walls represent the bulkheads that are inside those tunnel elements, which obviously are meant to make sure the tunnel does not flood, need to be dewatered. So you can do that by using a pressure pump, for example. By doing so, you will create a pressure differential between the inside of the tunnel and the outside environment. So what basically happens is that you use the force of nature to make sure those tunnel elements are connected towards each other. So in number 5, you can take away those bulkheads. They are of no use anymore. And you can install the secondary sealing solutions, which are omega seals. So in number 6, you can see 2 seals that are placed after the first seal has been provided. So when all those elements are lined out, you can start to backfill this system with sand and gravel. This is basically meant to protect the whole system from the environment. So that has to work for at least 120 years. That's mostly the amount of time a tunnel owner wants the tunnel to last. So here you can see a typical cross-section of an immersed tunnel. So most of the time in the middle of the waterway is the deepest, or that's the part where the tunnel's elements are going to be lowered. At the adjacent sides of those immersed tunnel elements, you will see 2 cut and cover parts. These are parts that are not being lowered in the water trench, but they are built in situ on that specific location. At the corners of those cut and cover tunnel parts, you will see a ramp area, and those parts are being interconnected with the existing infrastructure or the infrastructure that's going to be built later on. So now the question arises, why actually building an immersed tunnel? Because there's so many other options to cross from point A to point B, obviously. Well, it depends on what your situation is, obviously. But there are a lot of advantages for immersed tunnels that will speak for this technique. At first, it's very suitable for short, shallow crossings in soft soil. Also, the shapes are very flexible in dimensions, because you can imagine you can just lower different type of cross sections. And if you want to provide a tunnel that has different lanes, you can do that. You can just construct a 6-lane cross section and lower that into the trench. And you can also change those 6 lanes to an 8-lane or less, obviously. That's something that cannot be done so easily with a bored tunnel construction. Another advantage is the land reclamation opportunities it provided, because you have to suck out land in order to make the trench in which you place your immersed tunnels. This land can be used simultaneously to create artificial ground or artificial islands in the surrounding area. And last but not least, it can be economically very feasible to use this kind of technique too. So mostly these type of techniques are used in areas where there's a lot of water, a lot of urbanization going on, and the soil is a bit softer than usual. So keep this technique in mind when you are designing for these kind of circumstances. Now I will show you a short movie introduction of the immersed tunnel technique that will hopefully clarify everything I just said. So here you can see the building. So the big GINA seal will be installed on the dry dock by clamping it into place. So you will use steel end frames, steel clamping systems to make sure the GINA seal will stay into place. You bolt it down together, provide enough clamping force in order to make sure it stays on place. So here you can see that obviously. There is more compression. Now we can see the omega seal being clamped into place, which is basically the secondary sealing solution. And many more are to follow. And when everything is done, you will see that an infrastructure is being created. So I hope this animation clarified everything related to the construction of the immersed tunnels. Here you can see a real-life situation or example of how such an element is being constructed. Here you can see a tiny worker in the front of the element for scale. You see it's rather big. This is an example of an immersed tunnel construction in the Hong Kong-Zhuhai-Macau bridge tunnel connection. Here you can see those tunnel elements are being floated after the dry docks are built up with water, and then those elements are located to the right location. So what can we see about immersed tunneling over the years? A lot of trends are being recognized at this moment. On the left side, you can see one of the first immersed tunnel elements that are being constructed during the Detroit-Windsor tunnel connection. They tended to be way smaller in size, but also in number, because when you would cross such a waterway, there were a limited amount of elements that were being interconnected. But nowadays you see that you can go as long as 32 different elements, and you see that those elements tend to be wider, tend to be longer, and tend to be more high as well. At the same time, we see a steady increase in immersed tunnels. On the right graph, you can see that there is a very linear progression in terms of new immersed tunnels. So there are different types of immersed tunnels, because at the Detroit-Windsor tunnel we saw that the first immersed tunnel was a steel tubed type of immersed tunnel, But in total, you can say that the concrete monolithical type of immersed tunnel is way more popular. It entails more than 50% of the total amount of immersed tunnels. And yeah, this technique is mostly used in Europe and mostly used in certain parts of Asia as well. It kind of depends on what the requirements are. Sometimes political pressure is also of huge influence in the decision making for these type of different structures. You can imagine if you're living in a country or a place where the shipyard industry is very big, that there is a big lobby for to make these type of immersed tunnels with steel shells. But when the experience lies more in the field of concrete pouring, you can imagine that people want to go with this type of tunnel. Another big advantage with concrete monolithical structures is that this technique is way cheaper to perform than steel type of tunnels. And the single steel shell, for example, is something you don't see that much anymore these days. Also, in terms of geographical spread, you see a big change happening at this moment. There's a major expansion visible in China. This graph is already a few years old, but if you would make the same graph at this period of time, you will see that China is definitely expanding, even more than can be seen on this graph. Sometimes things go wrong when you construct immersed tunnels. That's obviously not something you want to happen, but calamity is not a stranger to us. We have experienced different type of calamity in the past, and we do not run away for it, but we like to learn from those mistakes happening. So here you can see my colleague, which is in a building construction, and an inflatable type of steel was not performing anymore. So the whole construction site started flooding with water. There was just a combination of different things going on at the same time. Yeah, hopefully nobody got injured that day. However, this obviously has a lot of financial consequences when something like this happens. Eventually, everything worked out fine. We worked together with the contractor and the other parties involved and found the best solution for this small disaster, you could say. Calamity is also not a stranger back in the days. During the construction of the TAIym tunnel, there were 6 different floods during the day. During the second flood, there were even 6 deaths reported. And there was a lot of skepticism going on back in the day, whether it was even possible to cross such a navigable waterway. Fortunately, people just continued pursuing this type of technique. So that's the reason we are here today with the tunnels we have these days. So we should be grateful for that. So we talked a lot about steel and concrete. Now let's see how rubber fits in this whole story. When you design for immersed tunnel projects, there are a lot of different environmental impacts that can have an influence on your joint design. At first, for example, when you start building an immersed tunnel in a high seismic area, for example, you start making an immersed tunnel in Istanbul, you have to take into account that there can be a lot of dynamic activities influencing your seal. So you have to make sure those tolerances are lined up with your design. Also, when designing with concrete, those elements tend to expand and retract over its lifetime, which are also tolerances you have to accommodate into your design. Ground solidation over the years has a huge impact on your joint design too, and at the same time you will have water pressure that ranges from high tidal pressure to low tidal pressure, and it can just affect during its lifetime. When you design a tunnel for 120 years, you can imagine there's a huge range in water that it has to accommodate. As I mentioned, a general lifetime lies between 100 and 120 years for these kind of tunnels. It depends who the tunnel owner is. So if we look at the rubber as a building material, on the lower left corner, you can see how the rubber generally arrives to our factory in Ridderkerk, like big sleeves of plastic layers, rubber layers. rubber is a unique compound. It's an amorphous polymer in a vulcanized state. And the general ingredients that it contains are listed on the right side. So it has a lot of elastomers, obviously, carbon blacks, hence the black color. Sulfur is needed to make sure everything can be vulcanized. It basically functions as an accelerator, but you can combine it. It's basically a receipt for the things you want to build. If you want to build a rubber that's resistant against ozone, you probably need different ingredients. If you want something that is resistant against oil or gas or something else, you will need to have a different type of receipt to come to the right compounding. So this makes me hungry, but this is actually a metaphor of what rubber as a building material is. So in an unvulcanized state, the polymers are basically just floating around. They are not connected with each other. At the point you start vulcanizing this rubber material, you will see that the chains of the molecule are going to get interconnected. So you basically create one very long, big molecule that is basically just one molecule. So if you see a seal, it's basically one very big interconnected molecule that has side chains. So what's the reason that rubber is so unique? And why do we need these properties? And how does rubber differentiate to other polymers? I will give you a quick overview of what it means. So here you can see three very general polymer groups being displayed. On the right side, you can see the crystalline polymers. They have, if the temperature rises, you can see that there is a long-term behavior has kind of a problem. In other words, the material starts to melt, which is obviously not something you want to happen if you're using it as a building building material. On the lower picture, you can see amorphous plastics. They behave a bit differently, but the same goes as for the crystalline polymers. Eventually, when the temperature rises, they start melting. The thing with rubber is when you vulcanize the material, it creates a very durable and dependable behavior. So you create a vulcanization plateau. This vulcanization is non-reversible. So when you vulcanize your material, it cannot go back to the original state it was, which is something that you want to happen, obviously. So here you see the engineering bandwidth of a vulcanized piece of rubber. It's a quite big range. And there are also some other rubber characteristics you have to take into account because it's a very unpredictable material at the same time, which means it's a non-viscoelastic material. In other words, it does not behave like Hooke's law. That makes it at the same time very difficult to perform TAIym analysis on, for example. A few of those material characteristics are being displayed over here. On the right side, you can see the hysteresis happening in a rubber material. If you see that the stress rises at P0, it starts rising to P1. And then when there is an unloading of your compression, you see that the stress and stretch ratio differs. So the energy is being dissipated within the material. The compression set is also something that influences the material of rubber, which means if there's a dynamic compression of the material, the rubber does not go back to the same position it originally would reach, which means the material behaves differently than originally was anticipated. Also, relaxation takes a huge part in its unpredictable behavior, which means when you have initial compression of your GENA seal or another type of seal, the stress will lower over its lifetime. So those are all different type of characteristics you have to keep in mind when designing for these kind of purposes. So here you can see a typical table of rubber properties that you often see when you're involved in this market. These type of properties are often used as quality assurance. A client often wants to know what he buys, what type of properties are allocated to which functions. It also builds comfort with your client when you can communicate what type of properties it entails. At the same time, you can also see it's been used as a strategic tool because all those properties are being tested by different types of standards. We have, for example, the NAN standard in the Netherlands, but you also have the DIN standard in Germany. You have the GB standards in China. They're all different, and you can play along with that. So if, for example, one manufacturer of seals complies to certain parts of norms, in order to compete in the same business, you also have to comply to their standards. So you can say it's a quality assurance tool, but also a strategic tool at the same time. A small recap. So what does make rubber unique? It's mainly its durable, long-lasting rubbery state that is being created due to its amorphous vulcanized crosslinks. And that will create a very dependable, very predictable, reliable building material that can be used to make these concrete steel constructions watertight for a very long time. So it's time to get a bit more practical. As I mentioned before, those tunnel elements are being constructed on land, and they will be lowered into a trench. So on this picture, you can see tunnel element number 1, tunnel element number 2, and number 3 as well. Those small vertical lines being displayed are the segment joints, and the bigger one with a red dot around it is the immersion joint. If we zoom in a little bit more, you can see you can distinguish 3 types of seals, number 1, 2, and 3. So we have the GINA profile, the Omega profile, and the Waterstop. Maybe you can maybe give one to me.
Yep, here we go.
So this is the big guys, one of the big guys, the GINA seal. We have a membrane seal, so this is basically not a compression seal. This seal will be constructed on the inside of the tunnel construction. Then, number 3 is the Waterstop, which is a joint you will pour into the construction, so it's not visible. I mean, if you construct it well, it's not visible at the end anymore. Yeah,
nice
what's that?
For at home.
Yeah, for at home, exactly. It's a smaller version of this GINA profile. As you can see, it has a tiny hole in it as well. That is meant for, you can produce it easier due to less vulcanization time. And at the same time, you will create easier initial compression because, yeah, it behaves differently, obviously. Here you can see another seal. This is the inflatable seal. So this is a cross section. It's obviously is way bigger than being displayed over here. What happens is you place it into the construction, you will pump it up with water, and it expands, and it can be used as a temporary seal and also as a primary seal in certain circumstances. So the GINA profile, the big one. You can see that the GINA profile started out rather small and started developing over the years. So you can say it becomes bigger and fatter over the years, just like with human beings. And it actually follows the same kind of trends as the immersed tunnel construction. You already saw that the immersed tunnels were going to be wider, longer, and deeper. And the GINA seal design actually follows these kind of trends. So the GINA seal basically contains multiple types of compounding. The GINA over here looks as one big part of rubber. However, the nose often has a different, a lower type of compound than the body. And the flange often has the highest type of compounds because you want it to be hard to clamp it on the right position. Whereas the nose is smaller in shore hardness to create a bigger compression during initial compression. So we have 60-year-old samples of GINAs, which is useful, obviously. And we design these type of compounds with low relaxation because that has a huge influence in the performance of these type of seals. On this picture, you can see a typical cross-section of an immersion joint. On the top part, you see the steel end frame, the cross-section of that, in which the GINA seal is being constructed or clamped into place. A bit below that, you can see the omega seal functioning as a secondary seal, and this seal is being clamped in place with bolts. So what basically happens with the GINA seal, what does it need to do? So at first, you have a lot of compression that it needs to accommodate. High forces and pressures. Then you have large transition movements that has to do with the settlement I was talking about. So it has to do with these side deformations too. Apart from that, there's a lot of durability and environment that it has to deal with. So to put it into perspective, these are typical ranging forces you have to deal with. So we're talking about 150,000 kilonewtons compression that it has to take. It needs to deal with about 100 millimeters transverse axial deformation. That has to do with the settlement, mostly speaking. And then we have tested these seals, counting pressure up to 9 bars. We never applied to 9 bars, so mostly the deepest type of immersed tunnels are ranging between 20 to 45 meters in total. Last but not least, the lifetime requirement. So before we send those products to the client, they are often tested. This is a typical test setup we perform. It's difficult to test those seals one-on-one because they are just too large. You cannot compress the whole seal. We don't have the means for that. So we often go for the angles, the corner sections. Those sections are often are known to be the most fragile in the whole construction. So if we make sure those corner radiuses perform well, we can assume the rest of the seal will perform accordingly as well. So on the right side, you see a press. The GINA mock-up is placed under the press, and it's being compressed in the amount of compression you want to have. So within this construction, the pressure will start getting higher. So in the meantime, the pressure will build up in this construction. And a small leakage is visible. And there it goes. So as you can see, a lot of force is going on when there's a leakage occurring. So that's definitely not something you want to stand in front for. So this is another type of compression test. The one before is just a regular one where you compress the seal in the tensile direction. However, in this situation, for example, the client created a different type of steel end frame in which the plate was slightly tilted. So in this construction, we did the same type of performance test. We create documentation to accompany this type of tests to create and to give comfort to the client. So you can imagine you can create all different type of setups and ranging type of tests to make sure that you deliver the right product with the right validation accordingly. If we look at the omega seals, they also started out rather small and they evolved over the years. In the middle, you see the seismic omega, which was specially designed for seismic areas in Trans Bay. You can imagine if there is a seismic activity, there is a lot of movement of the ground. So you want to make sure that the joint remains intact over that type of things going on. At the same time, we see also the need for other type of seals. On the right side, you can see the M seal, which is basically the same as an omega seal, but then just way larger. And those seals are being applied in closure joints. I will come back later to the concept of closure joints, but first I will start talking about omega seals. So the omega seal, as I mentioned, is a secondary seal. It's not being loaded due to compression, but it's been loaded. It functions as a membrane basically to cover up the joint. We also have 60-year-old samples for these type of omega seals due to renovation works in Rotterdam. So that gave us a lot of information of how that particular seal was performing over the years. And we tested the seal for over than 20 bars of force. So inside the omega seal, you will have an inlay material. So the stress is not being distributed to the rubber material only. It basically is done due to the fiber construction inside. And the rubber layers are only meant for making the whole construction watertight, basically. So here you can see a typical cross-section of the omega seal. On the graphic below, you can see the GINA seal being compressed, and the omega seal is clamped on place later on. So what most of the time happens is that those anchors are already being pre-installed on site, and when the omega seal arrives on site, you only have to clamp it on place, and you have to determine what the clamping force needs to be to make sure that the omega seal will perform accordingly. And during that tightening of those bolts, you have to take into account the relaxation. So most of the time you have to retighten them after 10 days, after 2 weeks, and then most of the relaxation behavior is being taken into account. So this is an omega seal being installed. It looks a bit warped at the first glance. However, this is a perfect normal behavior of the seal. It kind of shows that this type of seal can accommodate a lot of behavior during its lifetime. So what probably happens within this situation was that during the positioning of the elements, they were slightly tilted. But that's something that those building tolerances are definitely something you have to take into account while designing an omega seal. So those omega seals are sometimes tested as well, especially when you create a special type of omega seal. This is a type of construction you can use for that. You basically place 2 omega seals next to each other, and you will higher up the pressure within those omega seals to check out where the failure mechanism is and to check out how the clamping system behaves over time. I'm aware that in India there are not so many immersed tunnels from happening. However, omega seals can also be applied in different type of constructions. For example, in a station box tube connection. It's a very useful tool. Basically for very weird, complex transition areas, an omega seal will perform very well. Right. So the omega closure joint, that's a special type of seal. You don't see that often, to be honest. So in this case study I'm showing over here, we had to make an omega seal that had to cover 1800 millimeters in order to deal with the tolerances it provided. So how does a closure joint work? When constructing an immersed tunnel, you will lower the elements accordingly. However, at the end, you will see that there is a stack up of tolerances that you are not sure about. And what happened in this situation, the client created a closure joint that could be extracted in order to make everything fit, which is shown over here. This was the closure joint being constructed. On the left side, the black area represents the M seal. It's being lowered in place. So this is how it actually works. On the left side, you have the elements. On the right side, you have the other elements. And in the middle, you will sink down this closure joint. And you can see, if you follow the arrow, that this part can be extracted and can perfectly fit between the 2 adjacent elements. As you can see, the weird sinus-shaped seal is that M seal. And it needs to be rather long to make sure it can cover the movement of the moving structure. It was quite challenging for us as well to create these type of seals. Here you see the production of two different type of M seals. On the left side, you can see the bigger one, which in total was 1800 millimeters. On the right side, you can see a smaller version of that. So the sinus shape is meant to create the harmonic movement, but also production-wise, it's useful because if you can minimize the total width of the mold, you can minimize the costs. So that also works. So you create those sections of ranging from 5 meters to slightly bigger, and you have to vulcanize those sections into place. So you will end up with a very, very long linear length of this seal, and then you have to vulcanize the corner sections to those linear parts. So for this project, it was very difficult due to the multi-curved structure it contains, which was definitely a challenge. However, we succeeded by doing so. Here you can see the mock-up structure on the left side on site. So we created a test setup and a mock-up structure to give the client validation and trust that it would work at the end. On the right side, you can see the vulcanization press that connects the two linear parts and make a close ring after all that could be placed on the concrete structure. At last, we have the cast-in seal, which is called the Waterstop. And the Waterstop being displayed here in red. Normally it's not red, it's obviously black with steel. It's been poured into place. This type of Waterstop is tested up to 9 bars and has the same type of lifetime requirements as the other seals. And those seals are used where dilatations are required. So you can think about worst case scenario of an immersed tunnel is often seen as a sinking ship. So when the ship goes down, lands on the immersed tunnel, you definitely want your structure to accommodate those movement in your tunnel. So this is the working principle of a Waterstop. You pour it in on one side, and after it cures, you pour the other side as well at the same time. On the right side, you can see that the Waterstop can accommodate a lot of shear movement too. This is definitely not a normal situation. In this situation, one of the elements started floating. So that's the reason why there's so much of a differential movement being visible. This is definitely not something that's required or wanted. However, you can see how versatile the material is and it can work. Oh, what happened here? Nee, hoger, hoger. Nee, hoger. Hoger, hoger. Hoger. Yeah, here we are. Sorry for that, little technical issue. So here you see the cross section of typical building, typical in situ situation. Here you see the segment joint being visible. On the lower part, you can see an omega seal being constructed, being clamped on into place. And as a secondary seal, you see a Waterstop being sunken in. It also often has also other type of seals that are accompanied. So in detail A, you see a smaller seal that gets rid of the dirt, that the dirt cannot enter the seal. So there are a lot of different options you can use for here. So for the Waterstop application, this is what basically happens. You pour the Waterstop in, and when there is a movement, so for example, when the concrete starts expanding or retracting, you will create a small joint opening in which the full rubber material starts to create an arch shape due to the water pressure in that direction. So the water pressure causes this arch forming, and it results in a reducing radius and thus also in stress decrease in the material, which is useful. That's something you want to have. The Waterstops, there are some challenges involved, obviously. One of those challenges are the transport and installation of these type of products, because it's rather fragile when you roll them up in a reel, and when you have them placed in the construction site, they're easily teared, for example. You have to make sure that doesn't happen. Also, air entrapment is an issue. So when you place them inside, air gets under those constructions, and you can have air entrapment and small cracks. So we get back later to that a little bit more. During the concrete expansion and shrinkage, you have a lot of elongation, also tensile strength within your Waterstop. As you also saw in the last visual, sometimes those elements or there's settlement going on, and you don't want your Waterstop to tear at that point. The rubber metal bonding is also of importance. It has to do with the tensile strength that acts on this Waterstop, and you don't want your rubber rupturing from your metal. So here you can see an example of air entrapment during the pouring of such a Waterstop, and you can see an example of how a Waterstop can deal with these type of settlements. There is a solution to make sure air entrapment and cracks do not affect your Waterstop that much. So here you can see the injection system with resin. So what happens is that you pump with 10 bars, you pump an amount of resin into your Waterstop, and that resin flow will follow the path of least resistance, and thus creates and fills up the cavities that can occur. Waterstops are also tested how they are performing. So we did dynamic cycling tests and static tests up to 9 bar. What we did is we poured these Waterstop rings inside concrete blocks, and we performed different ranging movements by also increasing the pressure up to 9 bars. And we wanted to see what the failure mechanism was and when it started leaking. So we are currently developing our Waterstops because, as I already mentioned, there are some difficulties with the injection possibilities. So one of the developments we are working on currently is the implementation of more injection possibilities. So you can imagine if you pour in a certain amount of resin at the beginning of your tunnel lifetime, you might encounter cracks later on. So we want to provide the extra opportunity to inject an amount of resin within the Waterstop, for example, after 20, 30 years. Another thing we want to take into account is the flexible injection hoses, because the current systems are rather static and difficult to handle. So if we could change that to a flexible option, it would be way more workable and easy to do the installation. Also, less injection locations would be beneficial, as it would save cost and the injection time would be limited, which is obviously something that would be needed and wanted. So to do a small recap, immersed tunnels are very suitable for short, shallow crossings in soft soil. That's something we discussed at the beginning. Some trends are being visible in this world. Immersed tunnels are getting larger, they're getting wider, they're getting deeper. And sealing products such as Gina seals, Omega seals, and Waterstop, they tend to become larger as well. They're just following the trend of the concrete constructions. And rubber is a very reliable, versatile material that can be used to build tunnels with in combination with concrete and steel. So those are the 3 main messages I would like to share with you today. I hope that was all clear to you. And we are still here for a bit to discuss and to answer all your questions. So thank you very much for listening. So hopefully hear from you soon on YouTube. Thank you very much.
Thank you, Nicas, for a wonderful presentation. It was really exciting.
Thank you, Sandeep.
So I would take a few questions from the audience now.
Yes.
Yeah, we already received some questions, quite nice ones. But before that, Nicas, thanks for presenting. Very clear. Also have a question. Of course, we know each other already for a while.
Yeah.
And you've started it in our company. In my case, I would say recently. Maybe for you, it's already a long time. But like everyone else, rubber is not something that's been taught in universities or in schools much. It has always been some kind of an alien material, unknown. And now you've been working with it for, say, over a year plus. How has your idea of rubber changed? Has it changed, and do you think it's an underappreciated building material?
Right. Yeah, I can imagine at the beginning when you're graduated from university, you definitely don't learn so much about rubber. That also has to do with the fact that it's so difficult to calculate with. So it's way easier to calculate with steel or with concrete because it's quite predictable, obviously. So I didn't know much about it. So what I learned most, I think, from here at the beginning, I really didn't know much about it, is that it's really important to have a lot of knowledge and experience with this type of material. So by gaining, while getting to using this material over the years, you get more acquainted to it, and I think you can be very, your knowledge start improving. So that's something I learned the most. It's a material that is very slow to understand, but it becomes very useful information after a certain amount of time. So I think your knowledge, as someone that has been in the field for almost 15 years, is definitely something to
still surprised sometimes what it does and how it works.
Yeah.
So, it's not for no reason that we sometimes call it black magic. But now to some questions from the audience. First question that popped in and therefore deserves credit. I think the question was, how does the rubber seals in tunnels, rail tunnels, stand up against fire?
Right.
So how could they resist fire?
That's a good question. Thank you very much. So what often happens to make them fire resistant is that at first you will create an area where you will definitely not place your omegas, for example, just on the surface of the concrete structure. So you will have a small indent in your concrete construction in which you will place your omega seal, for example, or Waterstop. And then on top of that, you will create fire retardant plates. So that's in addition to the immersed tunnels. So we often work together with other parties that will provide these type of fire-resistant plates that will be placed on top over the joints to make sure everything is according to spec and can handle certain amounts of heat.
Then we have the next question. Divik, thank you for this one. How do you test vulcanized joints for integrity, especially if vulcanized on site? So how do you maintain? I mean, obviously, it's a good question because these are very vulnerable types of connections. So how do we assure that these joints are done correctly?
If you vulcanize on site?
Vulcanized on site or vulcanized in general, I guess.
Yes, so it's a good question. So at first we have a working principle going on. So we have a test protocol or also a vulcanization protocol. So we have people that are very knowledgeable and experienced that will do those weldings on site. They will do that according to a certain protocol. That's not so many things can go wrong, obviously. And often, if required, we can also do on-test tests. So in case of secondary sealing solutions, for example, omega seals, you can open them up. You can apply pressure between the GENA seal and the omega seal to see how those welds are performing when subject to a certain amount of pressure. So I think it's a combination of steps. So one is the working principle, the experience, and then as well the testing on site can be a validation that your welds are performed accordingly.
Mm-hmm. Thank you.
Do you have to add something to about it, Joel, or from your experience on?
Yeah, I think you got it right. I mean, it's very, workmanship is very important. So working with rubber, if you have it done and performed, you need to make sure that workmanship is correctly done.
Yeah.
This can only be done by experience. So joints that are being made, especially joints that are being made on site, where you have limited amounts of testing, even though we can test, of course. Basically, we require that people have at least a minimum of a number of years of experience. And yeah, thinking about our team, you know, that travels around the world, double digits years of experience. So
yeah, for sure.
Really matters. Next question. Let's see. Ansul Sindwani, I hope I say it correctly. How these joints seal will help in a situation presuming there must be a level of difference due to horizontal vertical alignment from the start of the immersed section of the middle section of the tunnel. So I assume like maybe different preset. How do these joints behave? So how do they cope with the movements? Say that the omega seal has to be installed maybe at the misalignment from the start.
So if I understand your question correctly, how do those seals behave with settlement or with installation? Is that
yeah,
correct?
I think if I hope I get it correctly, it's like how to install them or use them, because the Gina gasket is already installed, so it has already deformed. But the omega seal maybe needs to be installed.
So when the Gina seal is already installed and maybe there's some misalignment with the pre-installed anchors, for example, sometimes you have to install the omega seal slightly offset, slightly from your nominal position to make sure it fits. So that looks a bit weird at the beginning because you will install the device, the omega seal, under a small offset, and it might look a bit strange, just like the picture I showed you with the twisted omega seal being in place. However, it does not function the omega seal's workable principle, as these kind of offsets are already incorporated into the omega seal design beforehand. So you have to make sure enough safety is left over to make sure these things can be accommodated into your joint design.
Yeah. And then we got a little bit update as there is a greater possibility of leakage due to execution issues in construction joint of precast elements. So yeah, of course that's correct if you precast them incorrectly, but that's the reason why the seals are there. I mean, rubber is there to accommodate for movements. It's the basic principle and purpose of these seals.
True.
More questions here. Yeah, how does it withstand corrosive environments like saline environment, salt, water?
Right. Yeah. So rubber is actually very can handle these type of saline environments very well. We didn't have a lot of negative experience with that, apart from the clamping system, obviously. So Gina seals and omega seals need to be held into place by the use of steel. And these type of materials can corrode over a certain amount of time. So you have to decide whether it's needed to use, for example, duplex material type of steels to make sure it doesn't start corroding. Or you have to make them thicker, or you have to take these kind of corrosions into account as well. But rubber as a material can handle these type of salinity very well.
Yep. And of course, if you have an environment which is dangerous to the rubber material itself, you can change the polymer, for instance. Say if there's hydrocarbons in place, then you switch from a natural rubber to, say, NBR rubber. But of course, then you might lose some of the mechanical properties that you might have. But then always you can, say, protect it through another means, or have two different rubbers combined into one seal.
Yeah.
Next question is how the rehabilitation of the rubber seal is carried out. So how do you rehabilitate joints?
So if one of those seals are being damaged, for example.
Yeah, basically how to refurbish.
It depends. Yeah, that's a good question. It depends on the type of seal, obviously. I mean, you experienced a lot of rehabilitations yourself as well. I think, you experienced obviously way more rehabilitations. I mean, it depends whether it's the primary seal or whether it's the secondary seal, because if there's only one seal at place, it's very difficult to perform rehabilitation. I mean, it can be done, but you cannot get out the seal anymore, obviously, because the construction starts leaking. So if you have damage on your GINA seal, you can vulcanize and repair them on site. Or you can, for example, add another seal over it. So you create an omega seal that will cover up this primary seal. So in those cases, you have to make chemical anchors in the construction. So anchors that are not connected with the reinforcement anymore, but you have to anchor them in place by chemical means, and then you can clamp it over the construction itself. This is a way of repairing or refurbishing, obviously. There are multiple ways, but I think mechanical anchors are one of the most common ways to rehabilitate such a seal.
Yeah, and luckily rubber has very good lifetime properties. So it is often usually the environment that needs to be refurbished rather than the seals itself. But the scenario, like you say, is different for each particular project, especially the way it is being installed, how easy it is to reach.
There's no standard way of
that's the challenge.
Do that. It's a challenge for sure.
That's a challenge. One we usually proceed with basically good inspection and make a bespoke solution for that specific problem that we might encounter.
Yeah, so when doing renovations, you always have inspection first with the client. So you want to know what the root cause of the problems are, obviously, because sometimes you don't even know whether the seal is leaking or whether there are, for example, cracks in the concrete. So knowing the root cause is very important to provide the right solution for the cause.
Yeah. And then we have another question from Mehdi Hosseini. What are the mitigating measures if the sealing of tunnels fail? So that's a bit of a catastrophe type of scenario.
Yeah, that's not something you want to
make sure everybody
want
can
to experience.
Yeah. But it's a good question because I mean nothing is forever and anything can happen.
Yeah. I think
Of course, there are pumps in place in most tunnels to take. It's not that every leakage or every failure is definitely catastrophic. I mean, the picture movie that we had earlier is quite of an extreme scenario. But usually there are two seals in place, so if one fails, you have another regular inspection to prevent these kind of things from happening. Good designs, but if things fail, for example, an omega seal is constructed in such a way that it's made of with woven fabric inside. So if it fails, it's usually a local failure. So you can still repair it afterwards. But in extreme cases, like with the movie, when we had to fix it, the mitigating measure eventually was to basically use divers to install a new inflatable seal.
It also depends what you consider a leakage. Do you consider leakage like a total catastrophe, or do you consider a leakage or failure just a tiny bit of water that seeps through?
Yeah,
that's a big difference.
And then you tackle it differently.
So it does. The one that's possibly shown on the movie does not happen that much, obviously, and that the seal completely loses function. So if leakages occur, what you do sometimes, it's often a tiny leakage that can be solved, by certain amount of resources. But it's not very common that people get injured or anything like that.
Yeah. Usually there is a protocol in place. If this happened, then there's like a fail tree.
Yeah.
So, well, obviously, a calamity would really be obvious, but usually the biggest problems are not those that are visible, but those that are slumbering, slowly progressing and becoming more of a bigger problem. So inspections is really important.
Yeah, for sure.
And the question from Jagdish, I thought Dutch names are tough. Jagdish Mahali. Do you have the sealing material which can be used as expansion joints? So I think those are like the ACME profiles or
we don't have them
joints.
on stock over here.
Yeah.
Those seals, we do not make them here in Ridderkerk anymore. but there are definitely other Trelleborg facilities that do make those type of seals.
Visit the website.
Yeah, if you visit the website, you can acquire a lot of information about these kind of other type of seals.
In any case, if there are any specific questions for certain products, you can contact us, obviously.
Yeah, you can always reach out. No problem.
Let's see, I think we've got through most of the questions. Yeah, so we've got the questions there. If there are any more questions, we're available. And as long as we're employed, we're available indefinite for questions.
Yeah, hopefully for a longer period of time.
Yeah.
Time will tell. All right, let's go back to you, Divik or Sandeep.
Yeah.
Thanks, Sandeep. Scott, we're reaching 1.5 hours. So, one for the audience, more questions, feel free to ask them now.
Perfect. Right, thank you very much for the time. It was an honor for us that we can share our story and knowledge this afternoon, and hopefully hear from you soon.
Thanks for the opportunity.